The following program contains intense scenes of mathematics. Viewer discretion is advised. Hello everyone, this is Gowzahr, the self-proclaimed physics detective, and today I'm talking about Star Trek Into Darkness. In this video I'll be detailing the mathematical equations and methods that I've used to investigate the Enterprise's fall from space to the Earth. As mentioned at the start of this video, there will be a fairly intense mathematical discussion to follow. If math is not your cup of tea, then I have a nearly mathless version that you can find by either clicking this cup of tea or following the link in the description below. Also, you should know that there may be some spoilers ahead. As a scientist, I was deeply concerned when, after the Enterprise's confrontation with the Vengeance, the Enterprise loses power and subsequently falls from somewhere close to the moon down to the Earth in a matter of minutes. So let's take a look at how long it would actually take. We start with Newton's law of universal gravitation. In scalar form, it can be written as, which tells us that the force acting between two objects is dependent on g, a value that represents the overall strength of gravity, m1 and m2, which represent the masses of the two objects, and r, the distance between the centers of the two objects. The next step is to invoke Newton's second law of motion, which states that the sum of the forces acting on an object will equal the mass of the object multiplied by its acceleration. If we assume that the Earth is the only object close enough to have a significant gravitational pull on the ship, then we can say that the sum of the forces acting on the Enterprise is just the force of the Earth's gravity, which allows us to combine the two previous equations to get, where in this case we're saying that m1 is the mass of the Enterprise and m2 is the mass of the Earth. This equation can be simplified to... And finally, remembering acceleration is the second time derivative of position we get, which is a second-order ordinary differential equation. Solving it analytically poses a surprising challenge, so I'm going to instead solve it numerically. For the benefit of those unfamiliar with numeric methods, I'm using Euler's method, it being one of the easiest to implement. Here's how it works. Euler's method breaks up a problem into small time steps and assumes parameters to be constant during each time step. For the problem at hand, that means that during any given time step, the acceleration and velocity are considered constant. So, we start with some initial position and velocity. For each time step, the acceleration is calculated based on the position. The velocity at the next time step is found using, where v sub n plus 1 is the velocity for the next time step, v sub n is the velocity at the current time step, a sub n is the acceleration at the current time step, and delta t is the size of the time step. A similar formula is used to calculate the position at the beginning of the next time step. And all we have to do is keep advancing time steps until we get a value for position that is less than or equal to the radius of the Earth, and then take the value of that time step to be the amount of time that it would actually take for the ship to fall that distance. All we need in order to get started are initial values for position and velocity. Starting with velocity, the ship doesn't appear to be moving until they lose power, so let's assume the initial velocity to be 0. As for the position, when they first drop out of warp, Sulu says that they are 237,000 kilometers from Earth. The wording that he uses is ambiguous enough that it's uncertain whether he means from the surface of the Earth or from the center of the Earth. So let's look at both. Writing Euler's method with a time step of 1/10 of a second gives times of 2 days, 8 hours, and 24 minutes for ship to center, and 2 days, 10 hours, and 41 minutes for ship to surface scenarios respectively. So under the assumed conditions, we can see that the ship fell to Earth much faster than it should have. So let's take things a bit further and see what initial conditions would be needed for the ship to reach Earth in a time frame more in harmony with the movie's depiction of the events. More specifically, let's look at what initial conditions will give a total time of 30 minutes. As would be expected, the farther the starting point, the higher the required initial velocity. The real question though is whether or not the crippled Enterprise could have moved into the necessary starting place and or gotten the required initial velocity. Well, that's all I have for today. If you have a theory as to how the initial conditions could have been satisfied, then let me know in the comments below. If you liked this video, then go ahead and hit that like button. If you're feeling adventurous, then subscribe to my channel. You can even follow me on Facebook and Twitter as a means of keeping up to date on my current projects. Well, once again, this is Gowzahr, signing off.